Hello, my good people. Welcome again to my YouTube channel or David Structural Hub. So this is a place where you learn, build, and innovate. So today I want to solve problem number 5 under three-moment theorem. And this is a question from a past paper. And the question reads, analyze the beam shown below using three-moment theorem. Hence, draw shear force and bending moment diagram, indicating all values at critical points. So, this is the beam. This is the beam, and the beam is subjected to anticlockwise moment, as you can see. Anticlockwise moment again is loaded with 10 kilonewton per meter. That is a UDL, and 60 kilonewton a point load, and 5 kilonewton per meter at the far end. So let's see how we can solve such a problem. So the first thing to do is to extend this line as usual to create a space to draw shear force diagram and bending moment diagram. After that, you will assume an imaginary span where the beam is fixed. So the beam is fixed at point A. So you assume imaginary span, which is OA. Then after that, we will start calculating our, now we will start solving the problem. So solution, we will begin by calculating free span moments. So free span moments. Free span moments. Let's begin by span AB. As you can see, span AB, it is loaded with a UDL. So the formula for free span moment is W L squared over 8. So this one is equal to 10 times 5 square over 8. So the answer is, you can punch your calculator. The answer is 31.25 kilonewton meter. 31.25 kilonewton meter. And then we proceed to span BC. Span BC, as you can see, span BC, it is subjected to a moment which is in anti-clockwise direction. So mu to the left or a moment to the left, it will be W A, no, it will be mu A over L, because this moment is causing a sagging at this point. So you have A and B. So it's causing sagging at A. So that is a plus. So this one will be, the mu is this moment, is 50 times A is the distance from where the moment is acting to the other end. So it's 2 over L is 5. 2 plus 3 is 5. Then you get your answer. So that one is 20 kilonewton meter. Then we go to mu to the right, or a moment to the right. This one will be minus mu B over L. So it means that this moment, which is 50 kilonewton meter, is causing hogging at B from here to here. So that one will be minus. So it's minus 50 times 3 over 5. So this one is equal to minus 30 kilonewton meter. And then we proceed to span CD. Span CD. Span CD, as you can see, is a simply supported beam, centrically loaded. So it has loading at the center. So the formula will be WL over 4. So this one is equal to 60 times L, which is 4 over 4. So we have 60 kilonewton meter. And then we proceed to span DC. Span DE. So this one will be minus WL square over 8. No, over 2. So it will be minus 5 times L, which is 2 square over 2. So this one will be minus 10 kilonewton meter. So this is the baseline. So we begin by AB. So AB, we had 31.25. So we approximate. So this one is a parabola. And that the H is the maximum bending moment. So that 1.25, like that. And then we proceed to DC. So mu to the left, we had 20 kilonewton meter. So we'll approximate along this line. So let's say 20 is there. So this H is what is 20. And then we have negative 30 to the right. So negative 30 will again approximate along this line. So negative 30 around there. So this is 30, negative 30. And then the next one is 60 kilonewton meter. So this is the 60 . So the H is 60, like that. And then the last one is negative 10. So negative 10. So this one will be a curve. So this is 10, like that. So after doing so, the next thing to do is to now apply three-moment theorem. So let's apply three-moment theorem. So apply three-moment theorem. So we will consider span OA, AB. So remember we said that for you to apply three-moment theorem, you will consider two consecutive span. So we begin from where our imaginary span is, which is OA, going that side, so OA, AB. And then we generate our three-moment theorem from this span we have considered. So the three-moment theorem will be MOLO plus 2 MA L0 plus L1 plus MB L1 is equal to negative 6 A0 x bar 0 L0 plus A1 x bar 1 over L1, like that. So that is our three-moment theorem formula. And as you can see, this beam doesn't have a varying I or EI. So the EI is constant. So automatically we will use our first formula of the Clapeyron theorem. So let's now calculate our areas and its centroid. So A0 x bar 0 is equal to 0 because this is an imaginary span. So A1 x bar 1 is equal to the area of this and its centroid. So the area of a parabola is 2 over 3 times base, which is 5, times height, that 1.25, times the centroid of a parabola is its length divided by 2, or base over 2, so which is 5 over 2. So the answer is 260 260.4167. That is the answer. And then the next thing to do is to insert these values into the formula, the known values into the formula. So you know that M0, L0 is 0. So M0, L0 is equal to 0. So we'll have 2 LO plus L1. LO is 0. So that one will be 0 plus L1 is 5. MA plus L1 is 5. MB is equal to negative 6 into bracket 260.4167 over L1, which is 5, like that. So we'll have 2 times 5, that is 10, 10 MA plus 5 MB is equal to, this one you can punch directly in your calculator to get the answer. So it is negative 312.5. So we call it equation 1. So this is equation 1. Equation 1. So let's proceed to another span. So we will have span AB and then BC. Then we generate our three-moment equation or a theorem from this. So we will have MA L1 plus 2 MB L1 plus L2 plus MC L2 is equal to negative 6 A1 x bar 1 over L1 plus A2 x bar 2 over L2. So that is our three-moment theorem. After that, we will now start calculating our areas and its centroid. So A1 x bar 1 is equal to the area of this and its centroid. So 2 over 3 times 31.25 times 5 times 5 over 2. So this one is equal to 260.4167, like that. And then we proceeded to A2 x bar 2. So A2 x bar 2 is the area and centroid of this. And as you can see, this one we have two triangles. So we'll start calculating our centroid from this point C, moving to B, because B is our common joint. So we start from this point, or from this triangle. It will be a half times 30 times 3 times the centroid is 2 over 3 times 3. And then remember, this one is negative because this one is negative, positive. So negative, like that. And then we will come to this another small triangle is a plus. So plus a half times the height is 20, the base is 2, and then the centroid is a third times 2 plus 3. So that's how it should be calculated. So if you punch your calculator, you should get minus 16.6667. So this is A2 x bar 2, like that. So after that, now we can insert known values into our formula for span AB BC. So we have MA L1, so L1 is 5, so 5 MA plus 2 into bracket 5, L1 is 5, L2 is again 5, so plus 5 MB plus 5 MC, because L2 is 5, is equal to minus 6 into bracket A1 x bar 1 to 60.4167 over L1 is 5 plus A2 x bar 2 is negative 16.667 over L2 is 5. So you can carry out the operation for this in your calculator. So if you simplify, we'll get 5 MA plus 10 MB plus 5 MC is equal to negative 292.5. So that is equation 2. We call it equation 2. equation 2. Let's proceed to span BCCD. Span BCCD. And this is our last span to consider. So we generate our formula, three-moment theorem formula from this span. So we'll have MB L2 plus 2 MC L2 plus L3 plus MB L3 is equal to negative 6 A2 x bar 2 over L2 plus A3 x bar 3 over L3. After doing so, you can start, or you can begin by calculating our areas and its centroid. So A2 x bar 2, A2 x bar 2. So A2 x bar 2 will be the area and the centroid of these two triangles. So now we will be moving from this side, going to the common joint, which is C. So we will begin calculating our centroid from this point, going to the other side. So the area for this triangle, which is positive, so it is a half times 20 times 2 times the centroid is 2 over 3 times 2. After that, we come to this one. This one is minus a half times 30 times 3 times the centroid is a third times 3 plus 2. So A2 x bar 2 is equal to, no, this is A3. No, it's correct like that one. So the final answer is negative 108.3333, like that. After that, we come to this one, come to that symmetrical triangle. So it will be A3, it's bar 3. So we'll have the area, a half times base, which is 4, times h, which is 60, times centroid is 4 over 2. The centroid of a symmetrical triangle acts at the center. So there's no need to use B plus L over 3. So it acts at the center. So that is it. So this one should give you to 40. After doing so, we can now insert known values into our formula or our three-moment equation. So we will have MB L2. L2 is 5. So it's 5 MB plus 2 into bracket 5 plus, this is 5 L2, then L3, 2 plus 2 is 4. 4 MC plus L3 is 4 MB is equal to negative 6 into bracket 2x bar 2 is negative 108.3333 over L2 is 5 plus L3x bar 3 is 240 over L3 is 4, like that. So if we can simplify this, we'll have 5 MB plus 5 plus 4, that is 9 times 2 is 18, 18 MC plus 4 MB is equal to, so this one, just punch it in your calculator to get the answer. So it will be negative 230, negative 230.0, like that. But MD was negative 10 kilonewton meter. This is our D. So MD here is minus WL squared over 2. And you saw that the answer was negative 10. So we will take this negative 10 and substitute here. So we'll have 5 MB plus 18 MC plus 4 times negative 10 is equal to negative 230, like that. So this one, if you open the bracket, you will have negative 40. Negative 40, when closer to the other side, it will change to positive 40. So it will be negative 230 plus positive 40. So the final equation is 5 MB plus 18 MC is equal to negative 190. So this is equation number 3. So equation number 3, like that. So we have 3 equations. You can solve these 3 equations and find the unknown values. So let's arrange the 3 equations in their orders. So the first one was 10 MA plus 5 MB plus 0 MC. So we had no value for MC. So we will introduce 0 to make it 3 unknown is equal to negative 312.5. The second equation was 5 MA plus 20 MB plus 5 MC is equal to negative 292.5. And then the final one, 0. And we introduce this 0 to make it 3 unknown. So 0 MA plus 5 MB plus 18 MC is equal to negative 190. So that is our 3 equations. So for you to make your work easier, find these 3 equations in your calculator and you will find the unknown values. So which imply MA is equal to negative 28.0 5.757 kilonewton meter. MB is equal to negative 5.3486 kilonewton meter, and MC is equal to negative 9.0698 kilonewton meter. So like that. So now we have our values for MA, MB, and MC. So the next thing to do is to start calculating our reaction. Let's now calculate our reaction. So for you to calculate reaction, you will split this beam, which is a continuous beam, into simply supported beam. So, and this is how it will look like. We have splitted our beam, our continuous beam, into simply supported beam. As you can see here, we have a moment of which we calculated. It is 28.577. From here to here is loaded with 10 kilonewton. And then here we have again moment of 5.3486. This moment was there initially, 50 kilonewton meter. We have another moment of 9.0698 kilonewton meter, a point load of 60 kilonewton. We have a moment of 10 kilonewton meter, then a UDL of 5 kilonewton per meter. So we'll start by calculating the action for this section. So this one will be R, this one will be RA, this one R, B1, R, B2, RC1, RC2, then RB. So summation of moment at RA is equal to 0. So summation of moment at RA is equal to 0. So we will have minus 5 RB1 because this RB1 is moving in anticlockwise direction, minus 28.5757 because this moment is moving in anticlockwise direction, plus this UDL 10 is moving in clockwise direction, plus 10, you convert it first to a point load times 5, and then the center is 5 over 2 because moment acts at the center of a UDL. So plus this 5.3486 is equal to 0. So if you can carry out the operation keenly by the help of your calculator, you will find that RB1, so this implies RB1 is equal to 20.3546 kilonewton. That is RB1. For RA is equal to 110 times 5 minus 20.3546. So the reason for this is summation of upward forces is equal to summation of downward forces. So for upward forces is RA plus RB1. So, and then for downward forces is 10 kilonewton per meter. It's a UDL. You convert first to a point load by multiplying that UDL by the distance. So it's 10 times 5. So RA is equal to RA is equal to 29.6454 kilonewton. Then we proceed to this section. So we sum moment about a point, so summation of moment at RB2 is equal to 0. So we will have RC1 moving in anticlockwise direction times the distance is 5. So minus 5 RC1. Then you come to this moment, which is 5.3486. It is moving in anticlockwise direction, so minus 5.3486. Again, we come to another moment, which is 50 kilonewton per meter in each direction, anti minus 50. We come again to this moment, 9.0698, in which direction? Clockwise. So plus 9.0698. So this implies RC1 is equal to RC1 is equal to negative 9.255 kilonewton. So this is RC1. Then how are we going to obtain RB2? So summation of upward forces is equal to summation of downward forces. So for here, upward forces is RB2 plus RC1, and the downward forces is 0. So as you can see, there is no force on top of this section, no force, so it's 0. So this implies RB2 is equal to positive 9.2558 kilonewton. So it will just change the sign from negative to positive, or you can carry out the operation. You take RC1 and replace it here, and then this one will cross to the other side. It will change sign from negative to positive. So let's proceed to this section. So summation of moments at RC2 is equal to 0. So from here to here, we have 4. And RD is moving in anti-clockwise direction. So we have minus 4 RD. Then we come to this moment, 9.0698. It is moving in anti-clockwise, minus 9.0698. We have a point load of 60 kilonewton. This moving in clockwise, plus 60 times 2. Again, we have a moment of 10, but this one will cancel out, because if you take this one, which is moving in clockwise, it will be positive. Again, you will come and take this one, which is moving in anti-clockwise, it will be negative. So it will cancel out. Or you can just say plus 10 minus 10. Then you come to this UDL of 5 kilonewton meter in each direction, clockwise, plus 5 times 2. We are changing it to a point load, times 2 over 2 plus 4. So is equal to 0. So this implies RD is equal to RD is equal to 40 point 2326, like that. So RC2 will be 60 plus 5 times 2 is 10 plus 10 minus 40.2326. So the reason is upward forces is equal to downward forces. So the upward is RC2 plus RD. And then the downward you have 60 kilonewton. And then you have 5 kilonewton per meter. You convert it to point load, multiply by 5. You get 10. So RC2 is 29.7675 kilonewton. After doing so, we will proceed to shear force diagram. So let's draw the shear force diagram. So this is the values for various reactions. So RA is 29.6454 kilonewton. RB is RB1 plus RB2. So the answer is that. RC is RC1 plus RC2. So this is the answer, and then RD is 40.2326. So let's begin drawing our reaction. So RA is 29. So we approximate here. So 29.6454. So you'll take 29.6454 minus 10 times 5, which is 50. So it will give you negative 20.35. So negative 20.3546. And then you will join by a diagonal line because it is IODL. And then your answer, which is negative 20.3546, add RD, which is 29, plus 29.6104. So you'll get 9.2558. So it is positive. Positive is always above the baseline. So that is 9.2558. So this one will be constant up to the next loading, which is RC. So plus RC, your answer, which is 9.5558 plus RC, which is 20.5117. So the answer is 29.7675. So 29.7675. And then it will be constant up to the next loading, which is 60. It is downward, so minus 60. That one is 30.2325. So 30.2325. And then it will be constant up to RD. So plus RD plus 40.2326. So it's 10.0001. So it's 10.001. So 10 minus 5 times 2, which is 10, is 0. So you draw a smooth curve. No, not a curve. You draw a diagonal line like that. So this is 10. So this is plus, minus, plus, minus, plus. Like that. So our shear force diagram is complete. So the next thing to do is to start calculating bending moment values. And before you start calculating bending moment values, we will identify this point and call it y. So let's call it point y. So we will have to determine this distance. Let's say x. Then the remaining one will be 5 minus x. So we have to determine the value of x because it will help us in calculating the values for bending moment. Yeah, for bending moment. So let's see how we will find or how we can calculate the value of x. So using the similar triangle rule, we know that x, which is from here to here, so x over the height from here to here, 20.3546 is equal to 5 minus x over the height from here to here, 39.6454. If you simplify correctly, the value of x is, so the value of x, which imply x is equal to 2.0355 meters. So this is 2.0355. So this one will be, you get the difference, you minus, it will be 2.9645 meters. So having done so, you can now start calculating values for bending moments. So bending moment values. Bending moment values. So we start at point A. So bending moment at A we calculated, and it was negative 28.5757 kilonewton meter. Bending moment at Y. At Y will be the bending moment at A, which is negative 28.5757 plus the area of this plus a half times 29.6454 times base, which is 2.9645. So the bending moment at Y is 15.3 662 kilonewton meter. So that is bending moment at Y. Then we proceed to bending moment at B. So bending moment at B. At B will be bending moment at Y, which is 15.3662, then minus the area of this, minus a half times 20.3546 times 2.0355. So this one is equal to minus 5.35 kilonewton meter. So if you can remember, this was also our moment from the three equation moment at B. So we got 5.35 kilonewton. So you can now confirm the answer is correct. So let's proceed. So bending moment at, we are at B. Now at C. At C is bending moment at B, which is negative 5.35 plus the area of this. So it will be plus, the area is 9.2558 times 2 plus 3, 5 times 5. And then we'll minus this moment, minus 50. So this one is equal to minus 9.07 kilonewton meter. Again, bending moment at C from the previous calculation, we had negative 9.07. Let's proceed to bending moment at F. At F will be bending moment at C, which is negative 9.07 plus the area of this. So that is 29.7675 times 3. No, times 2. Because this distance from here to here is 2. So this one is equal to 50.464 kilonewton meter. So bending moment at B. Bending moment at D, we had negative 10.00 kilonewton meter. So now we can draw our BMD. Let's draw our BMD, bending moment diagram. So at A, let's first draw the baseline. So bending moment diagram, BMD. So at A, we have negative 28. So below is negative, let's say is there, negative 28.5757. Then at Y, so at A, we have negative 28.5757 is here. And then at C, we have 15.3662 is a curve. And then at B, we have negative 5.35. And then from B, we go to C. At C, you have negative 9.07. So a diagonal line like that. And then we have at f 50.46. So 50 is here. That one is a diagonal line, not a curve. So like that. And then we have 10. From here you go to 10. It's again a diagonal line. And then from 10 you go to 0. This one is a curve. Like that. So this is minus, plus, minus, plus, minus. So that marks the end of that question. And please don't forget to subscribe for more content. Uh, Subscribe, like, share, and comment. So we meet again in my next session.